hello again, everyone. So now I'm going to cover our recent attempts to build a kind of automated system for designing hyperdimensional computing circuits. So it's a kind of ongoing work that we have, and we call it the SupportHDC framework. So first, what is hyperdimensional computing? So hyperdimensional computing is also a brain-inspired method for performing machine learning tasks at the edge with very little energy and area consumption. And in this schematic, you can see, let's say, typical schematic of a hyperdimensional computing circuit, where the input data streams are first encoded into so-called hypervectors that we call phi here, through some very simple, let's say, operations such as additions and element-wise XORing and so on. And then after this encoding of this input data into a certain feature space, these vectors, these hypervectors, are then used to train the system. So learning is typically done by simply summing the hypervectors corresponding to each class. So for example, if I feed all the data from class 1 and I get all the hypervectors, the encoded hypervectors for class 1, by summing them all, I would get a form of centroid representation of that class. So that's why we would call it like the class centroid here. And we noted mu in this presentation. And then finally, during inference, when you get the input data and you encode them into query hypervectors, inference is done by measuring the similarity between this incoming query hypervector and all the, let's say, class centroids, all these mu vectors that were the result of the learning. And the class is inferred as the one corresponding to the centroid that maximizes the correlation with this incoming query hypervector. And so we talked about this encoding that we do, so from the input data into this feature space. And to be more specific, one of the most popular way of doing such encoding is the so-called binary spatter code approach. And in this approach, really it works as follows. So for example, you receive a certain vector x of dimension n, so maybe you have little n number of ADC channels in your system. So you have this vector x. And what you do is that you would, let's say, transpose each elements of that vector x into an associated hypervector. And these hypervectors are d-dimensional vectors of binary values, for example, +1s and -1s. And you do this association between value and hypervector using a lookup table. And this lookup table is initialized randomly at design time, really. So that's how it is initialized. And then once you get this encoding of that n-dimensional vector into an n times d kind of matrix representing it, then you go on to do, for example, some element-wise XORing operations of that encoding with some weight matrix, again, a kind of random binary weight matrix here. And then you sum along the dimension n to obtain a single d-dimensional hypervector that represents this vector x. Now, this is the most popular, let's say, encoding system that you have in hyperdimensional computing, but there are also other ones proposed, and for that I would refer to this excellent series of surveys proposed by Dennis here. So now that we saw a bit the basics of hyperdimensional computing, really we can turn our attention on the contribution that we really want to do in this presentation. So what we want to build is a computer-aided design software that can receive as input a certain target data set that you want to solve, a bunch of a priori constraints, for example, the dimensionality of these hypervectors. We'd also receive as input an objective that you want to reach. For example, you want to not only maximize the accuracy of the system, but also, for example, maximize the sparsity of the hyperdimensional computing circuit for hardware implementation purposes. And this, let's say, CAD software that we want to design would return the optimized encoder circuits and the optimized parameters of that circuit, as well as the learned HDC prototypes, meaning these hypervectors that are the result of the training process. Okay, so now let's get into our encoder design. So how do we design really the encoder circuit that projects these vectors of continuous value into binary hypervectors? So in machine learning, and certainly in classification, you're really interested in providing a nonlinear high-dimensional mapping of the input data into a certain feature space where the linear separability of the data is enhanced, meaning that this data that was previously could be classified with a kind of curvy line would be easily classified with some hyperplanes here. And a popular such mapping to do this kind of feature mapping is given by the random Fourier feature mapping here that you see in this equation here. The random Fourier feature mapping takes a vector x, takes then the inner product of that vector x with a certain random weight, adds a bias, which is also a random bias, also multiplies that product with a certain sigma constant, which is a tunable constant. And it does that d times. So with different random weights and biases, basically. So it transforms an n-dimensional vector into a d-dimensional, let's say, expansion of that vector, a kind of random expansion, random projection. And so, okay, we know that the random Fourier feature mapping is a very popular mapping that is used really a lot in, for example, supervector machine theory. And what we want to do is to build a hyperdimensional computing encoder that kind of, let's say, binarizes this random Fourier feature mapping into something that is more akin to hyperdimensional computing. So this is in fact inspired by some work that in fact proposed binary random Fourier feature kind of mappings. So the first thing that we do to make these cosines disappear really is to threshold them to +1s and -1 and 0. So if the cosine value is larger than a certain threshold t, we just assign it to +1. If it's smaller than -t, we assign it to -1. And if it's in the middle, we assign it to 0. And so by doing that, really the result of that feature mapping will again be something that is more binary-like and therefore more hardware efficient. So then after this thresholding, we still had these cosines. So in the previous slide, you saw that we still had these cosines here and we don't want to compute them. So what we do is that we remark that instead of applying the threshold on the result of the cosine, we can also simply apply it on the argument of the cosine under the condition that the argument also wraps around a certain constant. So it exhibits this cyclic behavior, in fact, of the cosine. And so what we do then is that we see that inside the argument of the cosine, we had this inner product between the weights and the input. An inner product can be computed as a multiply accumulate kind of operation. And so that's what we do. We compute this inner product as a multiply accumulate, but with the little difference that the accumulator, we allow it to overflow and underflow. And through underflow and overflow, it would give this cyclic behavior of the argument of the cosine. And so we apply this threshold then on the result of this accumulator that underwent some overflow and underflow variations. Okay, so now we got rid of the cosines there by binarizing them and let's say applying a threshold on their kind of argument, but we still need to binarize the input x here. So for doing that, we use something similar to the binary spatter code approach. So we just take inspiration from there, and we use a lookup table that associates each possible value that we have in this vector x, so that we consider quantized to be in bits. So it associates to each possible value a certain hypervector of dimension d initialized randomly. But in contrast to the binary spatter code, the way we initialize these vectors is that the probability of having a +1 instead of a -1 scales linearly with the input value. So for example, for the first one, we'll only have -1s. For the last entry, the largest value would have only +1s, but in the middle, the probability of having +1 and -1 is scaled linearly in order to basically represent that input value in the statistics of this vector. And after that, the last thing we need to do is to, let's say, binarize these weights. In the original random Fourier feature mapping, these weights are drawn from a normal Gaussian distribution. But what we do is that we draw them from a Bernoulli distribution with equiprobability of having a +1 and a -1. And so that's how we generate these binary weights. And now in the binary domain, the multiplication here can be done with a XORing operation. So what we do is that we do an element-wise XORing of that weight matrix and the encoded input x into those hypervectors, and then the summing along the dimension n to kind of play the role of the original inner product that we had in the random Fourier feature. And this slide summarizes all the encoding steps, where you see that in fact the threshold here that we set this threshold that we applied on the arguments, and also the sigma parameter that sets the speed of accumulation really will be automatically optimized by our CAD software. So those parameters will be automatically, let's say, searched through by our optimization routines. So now that we saw the encoding, let's see the training approach. So instead of doing the, let's say, typical training approach that you would see in HDC, meaning at least in most HDC works, where you would sum hypervectors and perhaps remove some of the hypervectors that would reduce accuracy, what we do is that we train, in fact, the system using least square support vector machine theory in reality. So given a certain data set of vector X, so we have n of such vectors in our data set with labels Y here. What we do is that we encode them into their hypervectors that we call phi of X, and we, let's say, solve this optimization problem, which is a mean square error minimization problem plus a regularization, so like ridge regression, really. So to learn this mu vector, which is the weight of that supervector machine, but in our context, it is the centroid hypervector, so the class prototype hypervector. So we learn this mu and this bias such that we can classify this encoded data set. So to solve this optimization problem, we resort to the theory of least square supervector machines, and we solve this problem in the dual space. So basically, when we do a Lagrange optimization, we can, instead of searching for the solution mu, so those HDC centroid vectors explicitly, we write down the centroids as a combination of all the encoded data in the train set modulated by some Lagrange multiplier alpha. And instead, you can show that by solving this system of equation here, you can retrieve the bias here and the Lagrange multiplier alpha, and then reconstruct these HDC centroid mu here. And so omega here in this regression matrix is the so-called kernel matrix, where each element is given by inner products between, let's say, pairs of encoded data in the train set. So by doing that, we can basically learn the class prototype vectors of our HDC system. We also have this gamma parameter that sets the balance between the mean square error minimization and the overfitting. And this gamma will also be automatically tuned by our SupportHDC kind of CAD software, if you want. Furthermore, we quantize the obtained HDC centroid vectors to B qubits simply by quantizing them. And during inference, what we do is that we check the correlation between an encoding, an incoming encoding. So we have in this incoming data X, we encode it using the HDC encoder as phi of X. And so we check this correlation plus the bias, and we choose the class that maximizes this. And in this slide, I want to bring your attention on the crucial role that the sparsity of the HDC centroid vectors play on hardware efficiency. So here we have an inner product. Of course, we can compute it as a sum of product here. And of course, if these entries in these mu vectors are exactly equal to 0, you can simply skip those computations. That is quite typical. But it goes further. Furthermore, what we can do is that in all the d-dimensional vectors that we have in our system, so the lookup table, the d-dimensional weights here along the dimension d, what we can do is that we can discard from memory all the entries that are aligned with the zeros that we have in the class centroids, because they will inevitably be multiplied by 0 valued. So by doing that, we can remove them from memory and save area and power. So now we get to the last, let's say, layer of optimization that we have in this system, which is this automated Nelder-Mead approach for, let's say, automatic parameter tuning. So, okay, we said that we have some, let's say, circuit hyperparameters like the sigma, the threshold T, and also the training hyperparameter gamma that sets the balance between overfitting and energy minimization. And these parameters, so gamma, sigma, and T, will be automatically found by the Nelder-Mead optimization technique. So what is Nelder-Mead? It's really a black box optimization technique that allows you to minimize a certain cost a cost that depends on, for example, hyperparameters, without knowing the explicit relation between these hyperparameters and the various quantities that you want to minimize. So it's a form of heuristical gradient descent technique that tries to extrapolate the behavior of the cost landscape from a few points that it measures in the cost landscape, if you want. And so it works as follows. Given an initial set of parameters, gamma, sigma, and t, you would do some train and testing of this HDC system given those parameters. You would get a few costs associated to each tuple, gamma, sigma, and t. And this bag of cost and this bag of parameters will feed it to the Nelder-Mead algorithm. It will return you a new set of parameters to try, gamma, sigma, and t, that will refeed back again for training and testing, compute the accuracy, compute, for example, the sparsity, and again feed it back to the Nelder-Mead algorithm. And by iterating like that, you would hopefully minimize this cost and found, let's say, well-suited hyperparameters. As a cost function, we are not only interested in maximizing accuracy, so minimizing minus accuracy, but also we want to explore the sparsity. So we want to maximize the sparsity of the class prototypes. And we balance accuracy and sparsity through a, let's say, balancing factor lambda. And in this slide, we really see how Nelder-Mead works. So this red triangle here, each corner of it, you can see it as a tuple gamma, sigma, and t. And as you see in the beginning, it tries to, let's say, extrapolate the behavior of that cost function inside that triangle and try to understand how to move downhill. So it's just a kind of heuristical way of doing a form of, descending downhill of a certain gradient. Okay, so now we get to the experimental results that we are, in fact, still doing, but some early ones here. So the first task that we tried to tackle was the Wisconsin breast cancer detection dataset. So the goal here is to detect, let's say, cancer from arrays of biomeasurements. And the way we compute the accuracy, so the test accuracy here, is through a, let's say, six-fold random train test splits. So we basically train the system 6 times using random train test splits. And we average the test accuracy along these 6 runs. As the, let's say, dimensionality of the hypervectors, we use 1,000 here. And we use as a bit width of the accumulator, we choose 8-bit. And as the precision of the hypervectors, we use 4 bits. And what we get here by sweeping, let's say, our desired sparsity. So remember in the cost function, we could decide how much we want to penalize sparsity. By sweeping sparsity, we can get this kind of curves where we get a Pareto front starting from 0.55, for example, here when it starts going down. And these curves give you all these, let's say, blue crosses are different HDC circuits that the system proposed that trade off accuracy for the prototype sparsity. And what you see is that as we increase sparsity, the, let's say, accuracy of the system diminishes as expected. We also did some tests with the cardiac arrhythmia dataset from UCI. It's more challenging because it has some missing values in the dataset. And we replace these missing values with 0. It's not the most, let's say, optimal thing to do, but for the sake of the example. And here we use a dimensionality of 5,000. And again, we can generate these accuracy versus sparsity curves. And again, we see that the trend is that basically when you augment sparsity, your accuracy would, let's say, diminish. We can also compare furthermore the performance of the obtained accuracies against some, let's say, publicly available spatter code approaches. And what we see is that we get some, let's say, a non-negligible boost in accuracy. For example, here it is quite clear. Okay, so I'm already at the conclusion. So as a conclusion, I showed you our ongoing effort for building a computer-aided design software that can, let's say, automate to some extent the design of hyperdimensional computing circuits. So it tries to introduce, let's say, approaches inspired by supervector machine theory, as well as a random Fourier feature mapping. Yes, I also wanted to say that our source code is released as supplementary material, so you can get the link in the paper. And as future work, we plan to explore better ways, perhaps to approximate this random Fourier feature mapping to hopefully increase the performance even more. Thanks a lot for your attention.